going in detail. I'll be talking in detail. So KCL means Kirchoff's current law. Kirchoff's current law is KCL. This is the KCL. Okay. So here what it actually states is that if you have a junction point in the circuit, all the currents entering must be equal to the currents leaving. Here the currents entering are I1 and I2 to this junction. So currents leaving are I3, I4 and I5. I3, I4, I5. So if you add these currents, that should be equal to this. So example circuit is like this. For example, you have a battery connected here. Current enters this node. This is the junction here. So at this junction, it splits into I1, I2, I3. So this I equal to I1 plus I2 plus I3. Afterwards, all these three join here. So for this junction, all these currents are entering and this is the leaving current. That's why whatever is the sum of the currents entering is equal to the sum of the currents leaving. This is called a Kirchoff's current law. Okay. We will be covering this application of that today in the Wheatstonebridge, meter bridge, potentiometer. So those are the important things we will be covering today. Then the second law, this is called actually, this is also called first law. This is also called first law, Kirchoff's first law. And this is also called Kirchoff's second law. What does the second law indicate is, you have, for example, these are called loops. This is one loop and this is another loop. Loop basically closed part in the circuit. So we always assume the currents to be like this. The currents going will be in a clockwise direction. Okay, so let's suppose this current I coming from here enters this resistance and splits into I1 and I2 at this junction. Okay, it goes into I1 and I2, but then our direction to calculate we will take like this. What that means is, here the sum of the, this is a voltage, this is nothing but a EMF. Okay? How many EMFs are there? So sum of the EMFs, sum of the EMFs in a loop, sum of the EMFs equal to the sum of the potential drops. Sum of the potential drops. So whenever they say potential drop is always when there is a resistance and there is a current going through that. IR is called a potential drop. The current multiplied by resistance is called a potential drop. So what is EMF? EMF is always for a cell. So whenever you have a cell like that, that means if we say like this, this is a EMF. So now if you look at in this loop, left side, here in this loop we have a one EMF, this one. In this loop there is another EMF. So here I could have written a different way, okay, but I chose to write the EMF are only one EMF in this loop. This is a loop 1. Okay, so EMF equal to, here also voltage dropping, here also voltage dropping. Here how much voltage drop? IR1. So that's equal to IR1 plus how much is the voltage drop here? I1 into R2. So that's an equation for this loop. Similarly for the second loop, you have V2. You can take V2 also. Now question comes, here I was writing positive to negative direction of current. This is one way of, sometimes colleges they say this. I would recommend using this. Sum of the EMFs equal to sum of the potential drops. So in this case V2 equal to, so what are all the potential drops? Now if you look at this, right, for this the direction of I2 and this direction both are in the same direction. Okay, so that one and this one is a different direction. Therefore if they are in the same direction, if you are opposite direction, you will just take just I1 R2. Opposite direction you will put a positive thing. Same direction you will put as a negative thing. So this is in the same direction, that's why you have put as a I2 R3. Okay. So this part of the confusion, if you get it, normally you will not get, but in case you get, this is the other way of telling. Okay. So if you go through this loop, I am going from negative to positive, right? I am traversing this cell from negative to positive. That's why I take it as a negative V1. Then this I am going from positive to negative. Always the current direction enters positive. Therefore this becomes a plus IR1. This is again positive. Therefore I1 R2. This is R2. Okay. So in this case I1 R2, this is in the positive direction, but then you are going here also I2 R3. So minus I1 R1 I said, right? Why I said minus I1 R1? Because this direction, this goes like this, whereas I1 goes in the other direction. They are opposite, and that's why this direction is opposite to this. Is actually confirmed, like always you should take the clockwise. So that's why this has become minus and this has become plus. And then here also you are moving from plus to minus. Wherever you are going plus to minus, I have plus. So this is what I mentioned and textbook also mentioned, and this is also another way of doing the Kirchoff's voltage law. So what are these laws for and where we will use this? That is the next step. Okay. So the next step talks about, suppose we are trying to, we actually learned the other day about all these things, right? BB, ROI, something like that, color code. So if the resistance is given, on that resistance, if you have all that rings based on that colors, you will just say this is the value of this is maybe 2.5 kilo ohms or whatever. This is one way of finding out. Okay. Of course, let's it will come in general in milli ohms, not kilo ohms. Okay. So the other way is measuring the resistance, measurement of resistance. So whatever we do, whatever electrical thing we use in our house or outside, wherever electricity is there and you are trying to connect something into the circuit, that something definitely will have a resistance. So how do we measure the resistance? For that purpose, there are two types of things, or only one thing, which is called a Wheatstonebridge. Wheatstonebridge. So in this bridge there are totally 4 resistors will be there. One resistor is a standard resistor and one of them is unknown resistance. That means this is what we need to find. The other two are always fixed values. Okay. So totally 4 resistors will be there. By knowing three resistor values, you will be finding out the fourth resistance, or the, so wherever you want to find the device resistance, maybe a kind of a TV or a small phone or small something, appliance, you want to find out its resistance. So since this scientist has proposed this arrangement, the Wheatstonebridge goes by his name. Okay, and it's an important thing. Lot of times from exam point of view also important. Okay, so you have practical also. I think the labs also will be there on that. Okay, meter bridge, Wheatstonebridge, and then the potentiometer. So today's discussion is entirely circling about around this only. Okay, so before we go into this Wheatstonebridge picture and all the things, have you heard about something called a galvanometer? Yes or no? So in the 10th standard when we studied, right, if you keep this, there are two things. One is a galvanometer. Sometimes they put with a G also inside. They put like that. Okay. The other one is an ammeter. Galvanometer will just allow you to detect that there is a current going through the circuit. How it detects? This indicator, right? You will have a dial like that, and you will have something like that, and you will have a 0 at center and some divisions like this. So you will have an indicator. So this indicator may move this side or may come to 0 or go this side. So this goes, let's suppose it is going like 1, 2, 3 or like that. So you have a circuit and you put the galvanometer there. Okay. So if this shows deflects to whatever, actually they won't have the numbers also. It deflects to the right side. That means current is going this side. If it deflects to the left side, then current is going to the other direction, left to right to left. Okay. So this is going in the left direction. So the deflection will allow you to find out that there is a current going through that path. Okay. So along with these 4 resistors, a cell and galvanometer, these are the things that are used in the Wheatstonebridge. Okay. So how the Wheatstonebridge looks like, and now we are going to that part of it. So this is how the Wheatstonebridge looks like. So if you, I think in the textbook, let me go through the textbook. It's page number 118, 119. 118, 119. Okay. So in that he describes basically application of Kirchoff's rules, Kirchoff rules or Kirchoff laws. So as I said, in order to find out the unknown resistance, the bridge has 4 resistors, R1, R2, R3, R4. So where are they? R1, R2, R3, R4. If you see, this is R1. So don't put randomly when you draw in the examination. Okay, R1 and R2 are in the same dividing here. Okay, R1, R2, R3, R4. Okay, because they have got the names also for each arm. Okay, so R1, R2, R3 and R4 across one pair of diagonally opposite points. That means I have put this EMF. This EMF is applied across. So the cell voltage E is across AC. That means these points, right, this A and C, I am applying the voltage, or the cell is connected, and that's why the voltage there is marked as E. So since I have connected this battery, as I said earlier, right, if I draw only one line, this is a cell. If I draw more cells, this is called a battery. More cells together is a battery. So here I am actually connecting the battery. Okay, so but it's a voltage, a battery voltage, you can call it as battery voltage is. So since the battery is connected here, this arm AC is called the battery arm. And between the other diagonal BD, we have connected the galvanometer. Therefore BD is called the galvanometer arm. Galvanometer arm. And now we have BC and the DC. BC is a place where we have the unknown resistance we connect here. So here you will be putting that appliance whose resistance we have to find. So this is called unknown arm, and DC is called the standard arm. So now he explains why they call it a balance, and how the balancing, why is actually there is something called a balancing. So before that, let's come to the discussion of this. We are assuming that some current comes from here, it passes and divides into I2 and I1. So this I2 again gets divided because it's a junction. Some current comes this side and some current goes this side. From here also some current can come this side, some current can come this side. So in a normal situation, this galvanometer will show a deflection. When the galvanometer shows the deflection, galvanometer shows deflection, then we call it the unbalanced bridge. Unbalanced bridge. So connecting like this 4 resistors itself is called a bridge arrangement. Okay. So then when you have a deflection shown, that means this is called an unbalanced bridge. In other words, if there is no deflection, then what we call it? Balanced bridge. So the bridge is balanced when the galvanometer is at the 0. So at that time, the condition what they prove, we will be doing that steps, is R2 by R1. This is under the balanced condition. R2 divided by R1 equal to R4 divided by R3. This is important thing, and this is under the balanced condition. This is the ratio. This is how the resistor values will be. Okay. So the 4 resistors relation, this is how we write them as R2 by R1 equal to R4 by R3, and this condition is called a balance condition for the galvanometer to give a 0 or no deflection. Okay. Now to understand what does it mean by balanced. So let's suppose this current going through this is Ig, whichever way, either this way or the other way. So when Ig becomes 0, then we call it as a balanced bridge. Okay. Now let's go to, we are assuming that we have this Ig equal to 0. So now I am giving the derivation part of it. Okay. So here is I. So I gets split into I is equal to I1 plus I2, and whatever current finally comes back to the battery. So at this junction, this I1 comes this side, and no current is going this side, right here. Since no current is going inside this, so whatever I2 comes should go here, and whatever I1 comes will go here. That means I1, I2 equal to I4 and I3 to I1. Have you understood these conditions? Okay. Now this is what through the junction, through the KCL we got it. Here this is a 0. This is the current entering. That's why I2 is equal to I4. This is a junction B. Okay. This is a junction D. I3 equal to I1. Currents. So this side is 0. And this side whatever, I3 plus 0 equal to I1. So we have applied the KCL. That is the first law, current law. Understood? Now when we apply the current Kirchoff's voltage law, KVL. Okay, so we can apply the KVL to this loop and we can apply to this loop also. So when we apply for the first loop, okay, so this, when I am putting this circle, right, this direction of this current, is it opposite to I1? Therefore, for the first, this loop we will call as a loop 1, we take it as minus I1 R1 plus, this is nothing but plus I2 R2, because this direction is same. Okay, this direction is same. So plus I2 R2 plus 0, because this is no voltage, right? So this entire thing equal to 0. And therefore you will get I2 R2 equal to I1 R1. I'll be writing this in the next page, because next page again we'll have to copy this picture, right? That's why I wrote it here. Okay, so here, so we are doing I1 R1 minus I1 R1 plus I2 R2 equal to 0. That implies I1 R1 equal to I2 R2. This is nothing but 2 equal to R2 by R1. Understood this? So the next one will be, we apply the same thing to this loop. Loop current will say, here again, see, this direction and I3 direction are opposite. So since I3 direction and loop current direction, loop current means that line what we are drawing, right? This line. Okay, loop current I3 direction, loop current direction, they are opposite. Okay, we'll get minus I3 R3 plus R4 equal to 0. So like the one last case we did, we will get I3 R3 equal to I4 R4. Therefore I3 by I4 equal to R4 by R3. But we said the same current, right? I1 equal to I3, but we know
I4 when under the balanced condition. That means when this Ig equal to 0. So Ig equal to 0. So that implies I replace this I4 and it is I1 divided by I2 equal to R4 by R3. So this is what our equation 3. So 1 and 3 are same, 1 and the same. Equation 1 and equation 3 are same. So I1 by I2 equal to R1 by R2 by R1. I1 by I2 again equal to R4 by R3. So combining 1 and 3, you will get R1 by, so R2 by R1 equal to R4 by R3. So this is balanced bridge. Balanced bridge condition. You have understood? You will be able to do on your own? Kind of. Okay.
So since we said R4 is the unknown resistance, so R4 is unknown resistance, therefore R4 equal to R2 by R1 into R3. This is how we should be doing in the numericals. Okay, so you look at the example what is given in 3.8, example 3.8 in page 119. I'll be running through that example. Let's see whether you understand there or not. The 4 arms of Wheatstonebridge in that picture have AB equal to 100 ohms, BC equal to 10 ohms, CD 5 ohms, DA equal to 60 ohms, and the cell voltage is 10 volts. What is he asking? Next page. The question is in the next page. A galvanometer of 15 ohms resistance is connected across BD. Calculate the current through the galvanometer when the potential difference of 10 volts is maintained across AC. So he is not saying it's a balanced condition. That means some current will go through that. So this example is the application of the Kirchoff's current law and voltage law. So mesh and the loop both are same. I am reading on the page 120. Considering the mesh BADB. So it is a loop we are considering. That means the voltages we have to see. 100 into I1, because to that 100 ohms we are sending I1. We assume that I1 is going. 100 into I1, and the galvanometer resistance also given. Therefore that resistance, which is 15 ohms, multiplied by Ig. Okay. Minus 60 I2. Why he put minus? Because that loop direction is opposite to that of I2. If you are having difficulty, then I will draw and explain. You are having difficulty to understand? Okay. Okay. So let's go. This is the same thing. We will try to actually put the values here. So you have, this is 15 ohms. This resistor is 15 ohms.
Ohms. This one is 10, right? 10. So we apply this one. This is an example question, right? So the current will be like that. Oh, 60. Yeah, correct. You're right. This is 60. So 60 ohms. So you see this current and I1 are in opposite direction. That's why I will put first that one. Okay. That means 60 into I1. So this direction and this direction are same, plus 100 I2 plus, why? Because this direction and this direction is same. 15, that is the internal resistance. Ig, that's a galvanometer current. All put together is 0. Any questions? Understood, right? So next consider the second one, BCDB. The second one, BCDB, the other loop, this loop. So here I4 and R4 is given as 10 ohms, right? 10 and 5. So this is 10 ohms. This is 5 ohms. So 10 multiplied by, actually we should go with the negative one first. So this is negative. Both are negative, right? So minus 5 I3. Got it?
and this is also minus Ig plus 10 I4 equal to 0. So now if you look at that in the example what he has given in the textbook, right, this is where the actual application of the Kirchoff law coming. I had put here Ig, but in the textbook if you see, he said whatever is this current going through, some I1, okay, I1 or I2 minus Ig. So 10 times of both the things, I1 minus Ig and minus 15 Ig. So 15 Ig is correct. Then for the remaining two things, he has got it differently. Are you seeing that or no? Yeah, his I1 and I2 are different. Our I1 and I2 are different, I think. No, exact. Yeah, his I1 and I2 are changed. Our I1 I2 is changed. In the book, he has got 60 I2. We got 60 I1. Okay. And then he puts that I4 is nothing but I1 minus Ig. So if you are having confusion on this step, let me explain this one more time. Okay, I am doing undo. I am doing from this part. This part is easy. I said first one you should take whatever is that minus 5 I3. This is the one. Okay, then into this, right, you are having two currents. One is this, okay, whatever is coming through this, and whatever is coming through this, as well as Ig. Okay, so one of them you have to consider, like for example, if I say this is the one I am getting here, so this one I4 becomes I4 junction B. Okay, let's I think go backwards one more. At junction B, I1 is I2 current entering. That's equal to I4 plus Ig. So what does this give? Because this we are considering Ig. And at this junction